Physics students of Earth, welcome to a discussion about mechanical energy conservations, not conservations, but conservation when springs are involved. Students in my classes have had discussions about a couple of what are called conservative forces. Conservative forces are forces that can act within a system, and when they do, mechanical energy is conserved. There are two primary conservative forces, one of which is gravitational force, and the other of which is the force that a spring applies. That's actually an incomplete statement because there are other conservative forces, like electrostatic forces can be conservative, and magnetic forces probably. Anywho, we're going to talk about a situation here where we've got an object that has been pressed up against this spring that's attached to a wall here on the end, and we're saying that here is the spring's or the object's equilibrium position. So when this orange object, come here you, is at the position shown, why am I bothering with all this? When this object is here and the spring is, at the length such that the object is there, the system, well, the object is in equilibrium, which means the spring is not applying any force to the object. All right, but we're saying here something has pushed this object to the left to compress the spring an amount that we'll call, well, why don't we call this an amount, a distance x. Notice we have the famous words released from rest, and that tells us that this object is not moving. At the instant after it's released, it has not yet begun to move. So there's no kinetic energy as part of this mass spring system, but because this spring has been compressed a distance x, there is an amount of energy that we can call 1/2 kx squared. And well, why don't we say that this amount of energy is that much? And thus this system has mechanical energy equal to the potential energy stored in the spring. Okay, now the system is released, or the mass is released, and at the instant that we're looking at here, this is now a distance x over 2 via careful analysis of this diagram. Now I'm going to call this U spring initial. How about that? The energy stored in the spring now, watch this, we can write as 1/2 k, well now we're at x over 2 squared. And that's U spring is 1/2 k x squared over 4, right? X over 2 squared is x squared over 4. Well, look what we have. We have U spring initial, and we've got divided by 4. So this is 1/4 of that initial spring energy, right? And that's the nature of the quadratic relationship involved between spring displacement and energy, right? So if we change spring displacement by a factor of 1/2, we change spring energy by a factor of 1/2 squared, or a factor of 1/4. Okay, so it's not a linear relationship between spring displacement and energy. There is a linear relationship between spring energy and the force that a spring applies, but not displacement and energy. So because the spring is compressed half as much, the energy goes down by a factor of 4. And well, we still have to conserve mechanical energy. This doesn't explicitly state it on the slide, but let us neglect frictional interactions between the block and the surface. And well, okay, that means that this system must have kinetic energy that's about that much, about 3/4 of the total mechanical energy. Okay, so when this object is now back at equilibrium, all right, well, what's happening is this thing has been pushed and pushed and pushed, right? There's a force. Well, how would I How about let me change that a touch. How about I draw a, come here, representation of the force, the force that the spring exerts on this object. Right now, let's say there's a force that's that big arbitrarily, right? Well, when the spring is at, so that's instant 1. At instant 2, the spring is compressed half as much. The force is half as long. So the force, well, is half as strong. And therefore, we draw it as half as long. So we'll call that spring force 1. Here's half of spring force 1. But this object is being pushed to the right. So this thing continually speeds up. So even though it gets back to equilibrium now, it's moving because the spring energy is gone, because the spring is back to equilibrium length. Mechanical energy still has to be conserved, of course. And so kinetic energy is, well, makes up all of the system's mechanical energy right now. Okay? Fair enough? Okay. Now, let's look at a case like this. We have a block that's pressed up against a spring. And let's assume, again, blah, blah, blah from rest. Would it kill me to say released from rest? Probably not. This thing is compressed some distance. Maybe this is our, notice there's spring length, here's springs. This apparently is what we would call the natural length of the spring. So here is the amount the spring was compressed. And so this spring stores some amount of energy. Well, if we call this height 0, we can state that the Earth mass system has 0 gravitational potential energy. The system is released from rest, so has no kinetic energy. So the mechanical energy of the system is only of the potential energy stored in the spring. Okay, what we'll have in instant 2 here, call this instant 1, call this instant 2. At instant 2, the spring has returned to natural length. This object is now moving at a speed maybe we can call v2. So u spring is gone. Spring is back to natural length. Object still at height 0, so Earth mass system still has 0 gravitational potential energy. Now this system, well, has to conserve mechanical energy. So it would appear that all of the energy is now in the form of the kinetic energy of the block. In instant 3, I bet a reasonable question asker would say this thing has now reached H max. Spring still stores no energy. Well, H max means instantaneously this thing stops and turns around. Stops, I say, and turns around. Kinetic energy of that block is 0. Mechanical energy, you guessed it, is conserved. And thus, that looks too tall. Gravitational potential energy of the Earth block system is equal to the system's mechanical energy. So we get a nice look at transformations of energy from U spring to K to UG. Or from U spring to UG, if we neglect our instant 2. We don't have to talk about instant 2 if we don't want to. Right? We can say the system's mechanical energy transformed from all potential energy stored in the spring to all gravitational potential energy of the Earth block system. Okay? Okay. Oh, this one's a doozy, people. So, boy, we've got a vertical spring things are tough. Let's do this. Let's define height 0, the bottom. All right, and let's say this is height equals, we'll call it H. You want to call it H? Yeah, sure. And then this is H max. Apparently I'm measuring all my heights from the bottom of the ball. Fine. So, okay. And of course, we're going to say released from rest. And let's call this instant 1, instant 2, instant 3, instant 4. We'll go instant 1, instant 2, instant 3, instant 4. Okay. All right. So what do we know? We know that at instant 1, we can confidently say this thing is not moving, it's released. That's at it's at height 0. So mechanical energy is all of the form U spring. Let's, I suppose, make it 4 bars tall. Mechanical energy 4 bars tall. Let's see, instant 2. Okay, instant 2. Well, you know what? I'm going to go to instant 3. Watch this. At instant 3, the spring I know stores no energy, right? Because, look, we're saying that this is the spring's natural length, L naught. That's the length of the spring when it is not compressed and therefore doesn't do any pushing and therefore can't change energy. Can't change anything else's energy. Well, we definitely know this, right? We know our mechanical energy is going to be conserved in every one of these cases, so we can just jump right to that. This is where it's going to get tricky, though. Now, we've got no energy stored by spring. We got that, right? We got our U spring is 0. UG has gone up, but so is K, right? This thing is higher than it was, right? We've gone up by this far. So this thing is also speeding up. Now, from instant 2 to instant 3, notice the spring is compressed half as much. Here's the compression from instant 1. Here's the compression from instant. I'm not saying that well. Let me start that over. Yeah, okay. So at instant 1, the spring was compressed this much. At instant 2, the spring is compressed that much. So we know that at instant 2, the spring has a quarter of the energy that it did at instant 1. Catch that? Just like that slide a couple slides ago, because U spring is 1/2 kx squared, right? We can say that U spring 1 is 1/2 kh squared, right? This thing went from this height compressed down at instant 1 to that height, what we called height 0. So that compression, there's our x for instant 1, that's called capital H. U spring at instant 2 is 1/2 k h over 2 squared, right? It's been compressed. There's the x2, here's the x1. x2 is half of h. So that is the same as 1/4 of 1/2 kh squared. What I did there was square the h, square the half, and here's the half squared, right? So that is 1/4 of U spring 1. So that means in instant 2, okay, we've got 1/4 of U spring 1. Is that okay? That's okay. Now the question is how much K and how much UG? Boy, all right, let's see. Here's where it's going to get tricky, I bet, because we have to be able to do this. We have to be able to say that at instant 2, this thing is h over 2 high. At instant 3, it's h high. So from instant 3, it's twice as high up as instant 2. So that means that UG3 has to be twice UG2 because, remember, UG is mgh, and if we double the height, we double the UG. So what if we did something like, all right, from 2, what if we tried this? Now, maybe don't draw yet. UG, what if we went from here to here? Okay? Well, that would mean K, all right, if we're going to conserve energy, it would mean K at 2 has to be 2 bars tall, right? because 1 plus 2 plus 1 is 4. Well, here, if we're going to conserve energy, and U spring is definitely 0, that means K is still 2. But that can't happen because, well, the spring is still pushing on the object, pushing F spring, F spring. That's going to speed the object up. So what we can't have is that kinetic energy didn't change. So that means that our red and green bars can't work. But watch this. I can make them work. Watch this. What if we said UG was like half a bar, and then UG is a whole bar? Yeah, watch this. Because now what are we going to get? Now we have 1 U spring, 1/2 UG, so that means 2.5 K. So here's 0.5, here's 2.5. If now we have 1 UG, we must have 3 K. Okay, that's good, because what have we done? We've still increased kinetic energy because this object is being pushed the whole time, still being pushed from instant 2 to instant 3. So that's good. That's good. And then if we say max height, well, that means no spring energy. It means no K. It means all of our energy is of the form gravitational potential energy of the Earth mass system, and things are happy. We're happy. I like that. So questions with heights changing while spring energies change, those can be tricky, as evidenced by this one. Okay, folks. So here, these are probably the 2 of the main ones. Let's do this. Yeah, let's say that this is a released from rest situation. Okay, we'll say released. Actually, we're going to say this one's released also. Released from up there on the ramp. We're going to neglect any frictional losses here. And now we can actually start to write conservation of energy statements. Okay, so if we say, because, well, the forces that springs apply are conservative forces, we can say that ME initial, that's an I, ME initial and ME final are equivalent. We can say, okay, there's K initial, there's potentially UG initial, there's potentially, it's also not a G, there's U spring initial, and there's K final, and there's UG final, and there's U spring final. Okay, so, well, now we have to say, why don't we assume that this is 0 height? That means this goes, and that goes. Well, released from rest means that goes. At maximum speed, that's going to be when this thing is, when the spring has done all the pushing it can do, when it's no longer compressed at all, the spring will store no energy, and what we're left with is U spring initial transforms into kinetic final, or 1/2 K X initial squared is 1/2 M V final squared, where V final is V max. Well, these we can multiply every term by 2, and we can say that V max, which is V final, is K X initial squared over M, square root. If you wanted, we could say that V max is X initial K over M. It's okay to pull out something that's multiplied by other stuff inside a radical. Okay, so that's true. That's a statement for V max. Don't memorize. That would be a waste of your time. All right. What you need to be able to do, people for whom this stuff presents a big challenge, is you have to notice things like, ooh, okay, I know what that means. Oh, that's going to be when, sure. Okay, so don't memorize expressions. Maybe memorize what are the meaning of stated situations. Okay. Let's do another. Here's, let's see, we can start ME initial equals ME final. This is a thing that's released from rest, slides down here and goes squish until it stops for just an instant when the spring is compressed the most it's ever going to be compressed. All right, K initial plus UG initial plus U spring initial, K final plus UG final plus U spring final. What stays, what goes? Well, okay, released from rest. In the beginning, the spring is not compressed or stretched at all. UG initial, though, if we say, well, why don't we call this height 0, and we'll say that this thing starts at a height h. Okay, so it's not at height 0 in the beginning. K final, right? We have to be able to recognize that at the instant this spring is compressed, the most it's ever going to be compressed, the object stops instantaneously before it turns around. This is also a case where in the end, the block is at the height we've called 0, thus there's no gravitational potential energy of the Earth block system. And we've got two terms left. All right, so we have M, G, H initial. Well, okay, H initial we called capital H. 1/2 K X max squared. Okay, so looks like 2 M G H over K is X max squared, and thus, yeah. Okay, folks, so we talked somewhat qualitatively, kind of qualitatively, but sort of quantitatively also, because we're talking about relationships and the nature of those relationships and how they relate to changes in one quantity, and, well, how a change in one quantity relates to a change in another. All right, so that's semi-quantitative. All right, but we're not writing expressions yet. We're talking about transformations. Right? There's a couple of basic transformation ones. Here we get into some, a bit deeper thinking about, what has to be true about energies from instant to instant, and then how we can make this thing work, make the bars the right size such that transformations work in the right way and still behave according to, well, how physics is going to behave. And now here we get into some more problem-solving sort of situations where we're using the actual expressions for different forms of energy to solve for a variable. Okay? Let's see. Here's a problem that's, well, maybe a bit of a doozy. Vertical spring questions can be tough, but a good one to try. My kids will try it when I see you next. Okay? Fare thee well, people.